Okay, so to begin with, I want to ask you to think about this sum, 1 add 2 add 3 all the way up to 100, and the question is, what is the quick way of doing this? So when Gauss was in primary school, he was asked to do this sum by his teacher, and he did it astonishingly quickly. And the question is, what was his method? So I'd encourage you to pause this now and think about that question, because I'm now going to tell you the answer, which is to combine the terms into pairs that sum to 101. So we can pair 1 and 100, 2 and 99, 3 and 98, and so on. Each of these pairs adds up to 101, and there are 50 pairs. So the answer is simply 50 times 101, which is 5050. Okay, so far so good. So this, I'm sure, also reminds you of, well, this is an arithmetic sequence. So we know a formula, Sn, for the sum of the first n terms of an arithmetic sequence. That formula is familiar. However, what's the proof of that formula? Well, it's essentially what Gauss did. Except what Gauss did has to be modified slightly, because we don't know for certain that n is even. So if n is odd, we need to, well, that's why in the proof of this formula we double the sum, because that ensures we have an even number of terms, and then we can use this Gauss trick to do it. So that's where the proof of that formula comes from. Okay, so we've seen that before, and we know the sum from k equals 1 to n of k is a half n times n plus 1, and that's for all natural numbers n. Okay, so we've seen that before, and we know how to prove that formula. But what we're going to do now is think about some slightly more complicated sums. So if we wanted to sum k equals 1 to n of k squared, how could we do that? Well, there are a number of different ways we could do it. Notice that when we summed k equals 1 to nk, we got a quadratic polynomial in n. So it might be sensible to look for some sort of cubic polynomial n that might satisfy this, something of the form an cubed plus bn squared plus cn plus d, and then somehow go about trying to work out a, b, c, and d. And that's a very sensible approach. There are a number of ways to work out this sum. Maybe so first maybe I'll tell you what it is. Normally I wouldn't do that, but here's the formula. So one possible proof is to prove this by induction. Induction on n. We haven't done that yet, but that's chapter 8 in the book. In the book it says, wait until chapter 8 to learn how to prove this, but that's deeply unsatisfying. So of course the number of alternative proofs, proof 2, is to essentially construct 4 simultaneous equations to find these 4 numbers a, b, c, and d. So that's going to be on the homework. And then proof 3 is we could, well, essentially set up some sort of telescoping sum. Again, I don't want to say too much about that because that's also a question on the homework. And then proof 4. There are various combinatorial proofs. Combinatorics is essentially about permutations, combinations, binomial coefficients, that sort of thing. Again, I'm not going to give the details here. I might put something about that on the homework. Proof number 5, there's a really nice visual proof in something called Proof Without Words. You might remember when we did proof much earlier in the year, we looked at some of the proofs in Proofs Without Words. And I'm sure there are more proofs. I mean, the standard way to do it is induction, but some of the others we're going to see. So essentially, I'm not showing you how to do this because you're going to do it for yourself. So, but this is a really important result. So obviously we can use this to work out different sums. For example, if we have something like the sum from, this time I'll use r as the index. If we have the sum from r equals 5 to 11 of, let's say, r plus 1 all squared, how can we work out this sum? Well, we can first expand the brackets. We can write it as r squared plus 2r plus 1, and then this is the same as the sum from 5 to 11 of r squared, plus the sum from 5 to 11 of, well, twice the sum of r, plus the sum of 1 from 5 to 11. Okay, and then, well, I mean, for this one in particular, probably it's actually just much quicker to put in the numbers 5 to 11 and add them up, but to illustrate how the formulas work, if we had 1100 instead, you couldn't do that. So we're now going to use the formula we just wrote down for the sum of r squared. So I'll just go on to another bit of paper. Okay, here we go. So to work out the sum of r squared, we're going to use the formula, well, first of all, because it's from 5 to 11, we can do the sum up to 11 and then take away the sum of the first 4 terms. So we're going to get 1/6, well, if n is 11, we get 11 times 11 plus 1 plus 2 times 11 plus 1, and then minus the sum of the first 4. Okay, so that's the sum of the first 11 squares, take the sum of the first 4 squares. And then we have twice the sum of r. Remember the formula for that is n over 2 times n plus 1. Okay, so taken away, that's the sum of 2r. And then the sum of 1, well, that's just the sum of 1 from 1 to n is n. So this time we just have 11 take away 4. And then we just need to simplify this. So let's see, 22 times 23 minus 2/3, 3 over 2. So is that 30? Not sure. Plus 66, 56 times 228 plus 7, and then we get the final answer, which I'm sure you can work out. I'll leave the details to you. Okay, so in this example we're first going to work out the sum of r squared plus r minus 2 from r equals 1 to n. We need to show it's equal to this expression here in terms of n. And the idea in this part is to use the standard results for the sum of r squared, the sum of r, and the sum of 1 in order to do this. Then part B, we need to work out the sum of this series. Presumably this has some connection to part A. Okay, so we'll first do part A. So we can split up the sum. It's the sum of r squared plus the sum of r minus twice the sum of 1. And now we can use the standard results we already have worked out. So this is n over 6 times n plus 1 times 2n plus 1 plus a half n times n plus 1 minus 2n. And then we need to factorize this. So what's a common factor? Well, n over 6 goes into everything. So let's take that outside of the brackets. And then we're going to have n plus 1 times 2n plus 1. And then how many times does n over 6 go into n over 2? The answer is 3. And then how many times does it go into 2n? The answer is 12. Okay. And then we need to expand all of the brackets inside here. So we've got 2n squared plus 3n plus 1 plus 3n plus 3, take 12. And then, let's see, that's 2n squared plus 6n minus 8. And then we can take a 2 outside, so we get n over 3, brackets n squared plus 3n minus 4. And then that factorizes as n plus 4, n minus 1, which is precisely what we wanted to show, so we're done. And then part B asked us to evaluate 4 plus 10 plus 18 all the way up to 418. Well, let's think about r squared plus r minus 2, because presumably that has some connection with this. Well, if r is 1, 1 squared plus 1 minus 2 is 0. If r is 2, we get 4. If r is 3, we get 10. So it appears all of these terms are the sum of the terms in this series, r squared plus r minus 2. So in order to find n, we need this to be equal to the last term, 418. Just wait for that to focus. So we're going to have n squared plus n minus 420 is 0. And then we can factorize this. So let's see. Actually, isn't the answer 20? Because n is positive, we know it has to be 20. So now we want to work out the sum from r equals 1 to 20. Well, actually r equals 0, because the first term, oh no, sorry, r equals 1 to 20, r squared plus r minus 2. Remember, when r is 1, we got 0, but that doesn't matter, that doesn't affect the sum. So, and then we can use the expression from part A. So we're going to get 20 over 3 times 24 times 19. And then what's that? 160 times 19. I think that's 3040. So that's the answer. Okay, so we're now on to the sum of cubes. If we sum from r equals 1 to n r cubed, we get a quarter n squared times n plus 1 all squared. Again, there are a lot of different proofs of this. The proofs of this are very similar to the proofs of the sum of r squared. So again, see the homework for the proofs. We will learn later, when we do induction, the standard way of proving this, but there are many other ways which will be part of your homework. Okay, and notice also that this is the square of the sum from r equals 1 to n of r. So that's quite nice. Is that a coincidence? The answer is no, not really. again, see the homework for some interesting questions about this. Okay, so now on to an example. So we want to show that the sum from r equals 1 to n of r times r plus 3 times 2r minus 1 is 1/6 n times n plus 1 times 3n squared plus an plus b, where a and b are constants to be found. So in order to do this, we can again use the standard results we know for the sum of squares, the sum of cubes, and so on. So we have the sum from r equals 1 to n of this. Well, let's expand the brackets first. So this is 2r cubed, and then 5r squared, and then minus 3r. So we can now use the three standard results to split this up into three parts and sum separately. So firstly, just split it up like this. Okay. And then if we use the sum of cubes formula, we have 2 over 4 n squared n plus 1 squared. And then the sum of squares formula, we have 5/6 n plus 1 2n plus 1, and then minus 3 over 2 n plus 1. And then we need to factorize this. We want to show it's equal to this. So notice again the common factor is 1/6 n plus 1. And then what do we need to multiply that by? So we need 3n plus 1 to give us this term. And then we need 5 lots of 2n plus 1 to give us the middle term. And lastly, we need to subtract 9. Okay. And then let's tidy up everything inside the square brackets. So we have a 6th n plus 1 times 3n squared plus 3n plus 10n plus 5 minus 9. Whoops. And then that's 1/6 n plus 1 times 3n squared plus 13n minus 4. So the answer is this. So A is 13 and B is minus 4. And we're done. Okay then, so to summarize what we've learned, we know these four different formulas. The sum from r equals 1 to n of 1, of r squared, and r cubed. You need to know these formulas. You do need to be able to prove them, but the way you're expected to prove them in the exam is by induction, which we will learn in a later chapter. So, but as I said, the proofs will be on the homework. Okay, and also you should know that if you want to sum, just as you've seen before, if you want to sum something like r equals 6 to 33, then the way you're expected to do this is to do the sum from 1 to 33 and then subtract the sum from 1 to 5. Unless, of course, the numbers are very small and close together and you can just add the terms quickly without using this. But usually, if you have a sum that doesn't start at 1, this is what you would be expected to do.